Auzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Hello, hi everybody. Welcome to week 9. So today I'm going to talk about the transaction and concurrency. So this is the content of this slide. So of course we will talk about two things here. The first one, the first part we talk about the transaction, and then the second part we talk about concurrency. So for transaction, we talk about the definition, of course, the what is the inconsistent state, and concurrency. We learn about the schedules. Problem is how to isolate the transaction, how to do serializable schedule, checking the serializability, scheduling policy, and implement it, and the level of isolation and the anomalies. So this module provide an introduction to database transaction and why they are important. So basically transaction A consists of a single statement that retrieve all product in the lawnmower category. And transaction B clearly captures a new delivery. It insert a new tuple into the supply tables, then increase the stock level of the product in another table. Transaction C is a single update that correct a misclassification of a product. So this the definition of the transaction basically is a logical unit of work on the database that transform the database from one inconsistent state to another. So inconsistent state we can consider a state that or a situation that where is no part of the database contradict another part of the database. Okay, I think so. Let me tell you in a simple way. Okay, you see my cursor mouse cursor. So this begin transaction. So this is the end transaction. Okay. For example, if you want to do a query, you want to do like some kind like a select or update, for example. Update. Okay, let's say we choose you want to do like update the database. And then you update database. When you update database, it will start from here. And then the result of the update will be come out or will be appear in the end of the transaction. Where is my mouse? I'm sorry. So I tell you again. Let's say if you want to use update command in the DML command, it will start from here, and then the result will be appear at the end of the transaction. So the duration between begin and the end we call as a execution of transaction. So that's why transaction we consider like a update command, and then there's a purpose we call that like that lah. So between begin and end transaction, for example, if you use a update command, so in the meantime the database may be temporarily in an consistent state during execution. For example, you want to update the table, you want to change the value name from Ali to become Abu. You want to update the data. What will happen is you start with begin, and then during the transaction, the database, the table will become inconsistent state. So this is the meaning of the transaction. Okay, this another example I give you in the graphical ways. So let's assume a company that sells tools and equipment that has these three relations in their database. One product relation, supply relation that store the deliveries of the product, and one for the current stock level of each product. When products are delivered, a new delivery tuple has to be inserted into the supply relation. The delivery increases the stock level of the product. Therefore, the quantity attribute for the product has to be updated in the stock level relation. If there is a delivery that does not bring the stock level up, the database is inconsistent. In the worst case, the company can no longer take order for the lawn mowers because, according to data, there is none to sell. So here, for example, this is the inconsistent state. You want to update 3000 here, but in the meantime, I mean between the execution, we call it an inconsistent state. Here still 0. Why? Because it's still on the way to update. Okay. So this is the meaning of the inconsistent state. Why it usually happen? This is normal thing. I give you in real situation why this happen. Because when we talk a database, usually the term when we talk the inconsistent that state, usually we talk about the the database. I'm sorry. When we talk about the database, the what we call the general terms that we think is database is huge, and then other thing is we need to think database usually is heavy. Why? Because database, in order to prepare the database, that we need to use a software. Usually software, there is a lot component in order to develop that kind of the system. So that's why the database system become huge, and then the processing, of course, it heavy. And then usually in database, usually we didn't put one data or two data, or usually we didn't put like 100 data. Usually we put around 1,000 or more than that, and we need to prepare the database that can store million of data. So in this kind of situation, usually database is heavy, and then we can see when you put something, for example, you want to click update, for example, we can see the transaction between it begins and it ends. So that's why we can see the inconsistent, and because it will do searching, and after that the software need to can do the update command or whatever. But the thing is, the database is heavy. Why? Because of the software itself, and then because of the SQL. That's why nowadays we most of the company, they prefer to the no SQL. So you need to prepare the new project. Actually SQL is a basic thing, and then after this, when when you go to learn further, you need to prepare the new technology. That's a normal thing. But what I'm trying to say, SQL is a heavy things. So that's why they have like some kind of word inconsistent system state, which is we have the beginning and the ending of the transaction. Okay. So this is property of the transaction. So of course we need to have the transaction should be the atomicity, consistency, isolation, durability. So these the properties of transaction are a vital cornerstone of rational DBMS. Basically, in every transaction is atomic. It only be executed is in entirely or not at all. It cannot be split up into smaller transactions. database must remain consistent, and the effect of a transaction should be not be visible outside the transaction context until the transaction is complete. Once a change has been made, it must not be lost. Database management system always treat individual statement as atomic action, even where they affect several tuples in the database. Transaction that consists of several statements need special attention. So, most rational database management systems start a transaction when they receive the first statement of a transaction, such as this insert statement. The transaction ends when the commit is issued. If there is problem with the transaction, perhaps because we lost connection to the database itself, or because there is a conflict with another transaction, all effect both the insert and the update statement will be undone. The database manager will issue a rollback, which also terminates the transaction. That's why usually when we do like we want to update the database, this I want to talk about in the software engineering part lah, because I know maybe you understand why we need to learn about the transaction, what happened. This actually, this is the process how to do the database, how to develop the database, because programming is a process like we are cooking a meal. There is no suddenly the meal is done and then finished already. No, we need to have like some kind like a process. For example, you want to make a dishes for the lamb soup. Is it a simple way we just put the water and then lamb only? No, of course not. We need to cook the lamb first. I mean, cook in a different plate, different pan first, and then we can pour it at the end. What I mean is must be a process. For example, okay, the transaction. For example, if you want to do like a update or edit the database, usually we didn't edit it in the real database. Usually we will copy the database first, the real database first, and we put in our computer. I mean, put in the local host, and then we do the editing. Then we do editing like update, editing everything, and when it finish, the code is good and everything is good, and then our manager said, oh, this code is good, the DMSQL is good, then we can implement this thing to the real database. Why? Because we are afraid if this thing, for example, if the problem like transaction loss and everything, it will affect to the real database, because the real database actually is running and is still accessed by million of the user at the outside. We don't want this happen. What we'll do is we do in the dummy first. We copy the real thing, the real database, and put in our computer, make it a dummy database first, and do like whatever we want to do. For example, insert or delete, whatever, update, and then if the problem like a transaction happen and the data loss, at least we can this thing, the problem will not make will not affect to the real one. At least we can do like we can backup and everything. We do like a rollback or everything. So that's why we need to learn about the transaction. Actually, the purpose of this learning the transaction is like we want to give awareness to the programmer, to the database developer, the dangerous of the transaction. If you handle this thing of issue correctly, what will happen? It will be happen to the database itself, because the database is hold the data, and each of the data is value of the money. For example, if you do, for example, especially we do like database for the banking purpose or cryptocurrency. each data is valuable. If not, you might be, kicked out from the company. So that's all I can say lah. What I'm trying to say is very important. So, okay. So this is the end of the transaction. As summary, we can say it's like a atomic transaction with the database which ensure database appear consistent to the world. So you want to make to create the awareness to ensure database is consistent. Then can be accessed by another user. So it can consist one or more SQL statements. So the first statement initiate the transaction, the commit a rollback statement, and the transaction. Many database connection work on auto commit mode by default, which make multi-statement transaction impossible. So at the end, we need to plan the transaction carefully to ensure no other users can see data while it is consistent. So this is the important part. Okay, so we go to the second part, concurrency. So in this module, I will explain about the why transactions are important, how database simulation can balance performance and isolation. The statement of different transactions arrive the database, usually from many users of the network. In this notation, an R is a read statement and a W is a write statement. The subscript number defined the transaction is a part of, and the letter in bracket is a variable that stands for the resource access. Usually one or more tuples or records, the sequence of statements are executed from a schedule. You can see that the schedule contains interleave statement from every transaction. Database do not try to execute statements sequentially. Often, the data a statement needs to is not yet in memory, and database management system has to fetch it from this. These operations are slow, and the processor can be used to process other statements in the meantime. So this example, T1 reads a value X in the database, then add 50 to the value and finally commits. T2 does the exact same operation, but because of the order of the statement, both transactions read the same initial value, which becomes the basis of the updated value. Therefore, the update of T1 is lost. Whenever a transaction reads a value first and subsequent change it, any other transaction that does the same can potentially override the value. We can say this is a conflicting statement because they belong to different transactions and access the same resource. In this example, T1 reads a value X in the database, then add 50 to the value. T2 reads the value before it is committed. If T1 then aborts and roll back the change, the value read by T2 never existed. This is particularly serious when other operations are based on the incorrect value, as it happened here. W2X updates the value based on the incorrect initial amount. In this example, T2 reads two set tuples in order to compare this set. T1 adds another set to the tuple before T2 can read the second set of record. When T2 finally reads the second set of the tuple, there are additional values and the value of X and Y no longer match because they belong to two different sets of the database. This is not as serious as lost update because the database is still in a consistent state even though it appears not to be. People think we have sold more than we have received from our supplier. Database management system have a scheduler to manage the final schedule of incoming transaction statement. A scheduler can delay a statement, which means that the following statement of the same transaction are also delayed. Each statement of transaction were delayed until all another statement have ended. Only one transaction could be processed at a time, and we will have a serial schedule. Serial schedules are always correct schedules because there is no interference from other transactions. If there are still mistakes in the database, the transaction were badly designed. Database management system never enforce serial schedules except by accident. They are too slow. Actually, the scheduler only has to identify for conflicting operation of different transactions that affect the same resources and take care these do not interleave. All the other statements can be processed in any order if they concern different resources. If the rules are observed, the schedule has the same effect as a serial one, with much better performance. A schedule which is correct and produces the same result in the database as a serial one, while not executing the transaction serially one after the other, is called a serializable schedule. In this example, if the statement arrives in the line above, T2 operation can be scheduled as they arrive because T2 does not conflict with other transaction. It works without resource Y. T3 have to wait until T1 completes because it reaches the same resources as T1 but in different order, which could lead to a deadlock situation. There are different definitions of serializability. So we can look at conflict serializability, which focus on serializing the access to database data several transaction access. When each of number transaction access separate resource and no two transaction attempt to access the same resource, the schedule is automatically serializable. When transaction attempt to access the same resources, we can use a dependency graph to determine whether the schedule is serializable. The first example has no edge in dependency graph. The second example is a slight alteration of the first schedule, in which T1 writes the value of X after T3 has read X, and T3 reads the value of Z after T1 has written it. Note the resource Z is accessed exactly the same way as in serializable schedule, with the exception of the commit between the write operation of T1 and read operation of T3. This means T1 and T3 are not concurrent and do not have to be considered for potential conflict. It's normal for database resources to be changed by different transactions, as long as transactions do not interfere with each other. So, looking DBS have read and write logs. Read log are so called share log because they can be shared across transactions. Everyone can read at the same time. Exclusive log are for writing and can only be held by one transaction at a time. Read logs can be upgraded to write logs, but only if the upgrading transaction is the only one to hold the read log. This is a locking DBS best defense against log updates. If a write operation is based on read operation of the same resource, the transaction has to request an upgrade of the read log to a write log. If this is not possible, the scheduler can, depending on the oscillation level, roll back the transaction. Versioning databases let all operations make changes to the copy of the data held by their transaction and store them in separate versions tagged with a timestamp. When the transaction issue a commit, it checks whether there are conflicting versions and roll back the transaction that has the latter version. In the example, T1 started work on X earlier, but T1 to commit first. The database can assume there are potential for data corruption. There are currently no purely version database on the market. Increasingly, database implement a mix of locking and multi-versioning. Oracle has already applied this principle. SQL follows suit of in the last decade. MySQL has used multi-versioning since it was taken over by Oracle. Basically, most current DBMS, database, use a mix of optimistic and pessimistic approach. When you program advanced features such as reservation for a resource, say room a booking system, you have to consider concurrency. According to the standard, the assumption level listed should work the way they are described. Read and commit is rather dangerous because you can read a value that may never committed and make decision based on these values. Read committed is safer and only lets other party to see the effect of a transaction which has been committed. So that means the value may change during transaction, making inconsistent analysis a potential problem. Repeatable risk refer from serializable only very slightly. In our isolation, you can only see the same value for a given item. However, new item may pop up. Naturally, you pay in performance for increased oscillation. Unfortunately, as in all meta SQL, this standard definition of oscillation do not apply uniformly in all DBMS. So, if you do the lab session previously, so I believe you all guys have been go through the lab in developing the SQL database, and by typing the commands, SQL commands query in the Linux. If you see when you're creating the database, creating the database or creating the tables, if you do the lab tutorial, you can see after you finish the coding, finish the type the coding that creating the table, you need to refresh the database. Refresh the data, the software first, right? You know why they need to refresh the database? Because of this. Because it not read as a real time. So that's why we need to understand, to have awareness about the concurrency things. What will happen? For example, you create the database here, and then suddenly people come, they want to update the other things in your database. What will happen? Of course, the things that they update might be clash, or the data will not updated. Why? Because it clash the process. So, as discussed earlier, serializable schedule are correct schedule, then therefore desirable. However, the SQL standard as well has realized that depending on the transaction, some interference can be allowed. Different oscillation level has been provided to give the programmer a chance to weight performance against oscillation. Interference between transactions are known as anomalies in schedule because in correct schedule, they do not happen. Whether an anomaly is actually a problem is for you to decide when you create your transaction. The cumbersome news is that very DBMS provides slightly different implementation of isolation levels. Oracle is an extreme example. It only implements 2 isolation levels included in the standard. The third is proprietary. Even read committed does not work as promised by the standard. It allows loss update. To make this worse, Oracle do not recommend you to switch to serializable when you have to ensure loss update do not happen. They recommend a workaround instead. So this is the practical example. We can see many applications on the web let you buy things. When you have browsed to the item you want, you often to get choose quantity up to the available maximum. Where does the application get the maximum value? Naturally, the available quantity has been looked up in the database. The available quantity. While you are making up your mind and checking out, many other users has ordered the same product. In this case, we cannot simply assume that the quantity is still the same as it was in the time of the transaction 1. The application has to check again when it processes the order, which does in transaction 2. Some people think locking the quantity until the user has decided is a good idea. This will not work because, as we remember, the locks belong to the transaction. When ends which end here, you may think we can combine T1 and T2 to make the lock less. This is very bad. It assumes no one else can even browse to this item while a single user is looking at it. Because we have no idea what happened in the database while the buyer was checking out, we have to recheck the available quantity to ensure the order can go ahead. The question is, will the database manager ensure that it does not change between the read and the write operation? They depend on the DPMS and the current isolation level. Different DPMS have different default isolation level. In many cases, the default isolation level does not guarantee that other transactions cannot change resource in the middle of this transaction. MySQL default to repeatable read and is therefore the only one among 4 DBMS that handle this problem automatically. So, in many booking applications, have to establish the non-existing reservation before offering the resource to user. In this case, let's assume we are booking a room X at time T. We have established in T1 that no booking Y exists for room X at that time, and other user booking. In second transaction, we would like to store the booking. As in example 1, we have to recheck whether anyone have made booking in the meantime. This time, the problem is more complex because we have to prove the absence of a row. After the repeat check for the absence of the booking in the R2Y, again we have the problem that might be changed between the queries and our addition of new booking. In this case, a new row could appear in the middle of this T2, known as a phantom. If you remember the association label and the anomalies they allow, you will conclude that only serializable can save you from phantoms. Unfortunately, light is slightly more complicated than this. First, you have to check whether this is the best approach for your database. Fortunately, there are 3 problems you have to take care of. First thing, an existing table changing in the middle of your transaction. Second, a non-existent tuple appearing in the middle of your transaction. And then the last one, likely analysis reading different version of different entry that should match. Sometimes the cell level by itself does not guarantee the absence of anomaly. You have to use special SQL command like select for update in Oracle. So, as a summary, we can say when you use transaction, statement arrive at the schedule of database without regard to the transaction they belong to. Processing one transaction at a time in serial mode guarantees a correct schedule. Schedule can be equivalent to a several even when statements from transaction are interleaved. Schedules are serializable when their outcomes equivalent to those of serial schedules. As default, DBMS directs scheduling rules even further, risking anomalies and the interest of better performance. Programmers have to be aware of the situation which they have to set isolation level especially to avoid database inconsistent. Okay. Basically, what we learn in this slide is all about we want to increase the awareness to the programmer, because if we want to build a database system, there are the things that we need to do to understand about the transaction and concurrency. Why? Because there is no one hand only that will touch the database. What the means of not one hand? The meaning of not one hand means the meaning of the not one hand means there will be a multiple user is access the server, the database in the same time. Also, maybe at the time a server engineer or network engineer also serve the database in the at the same time. And then this thing, I mean the stakeholder, for the stakeholder, they are do like operation, maybe like update or select or book or add information to the database. What will happen if the user A, for example, in the Asia, I think this uh, good thing, not good thing, this best example I can give to you. For example, in Asia system, there's a booking ticket, right? Okay, you want to go to the Kuala Lumpur. Okay, first guy. Okay, first guy want to book. This is the last ticket. This is the last ticket. This guy want to book the ticket, and then suddenly me and other guys want to book the last ticket. What will happen? Can I book? I see in my screen only one left. Other people also see one left. Three people see one left, and then we want to fight which person is get the ticket by our own device. Of course, in the system, maybe we can put in this case we can put like a, after we book the ticket, the system will check whether other people have booked it or not for the last ticket. Why? Because this is involved of the money. Of course, if I book, let's say if three people book and then we already pay it, and then when they go to the flight, just only one ticket, only one seat they are providing. So it will be big problem to the Asia itself, right? So that's why we need to have like some kind like algorithm that can check whether is it this ticket is booked under other people or not. Why? Because this is because of the concurrency. Because there is not one hand that touch the database. There's many people. As a programmer, we need to understand about this kind of the situation. Okay, I think that's all. So we can go to the open question. So this I think we already done in the previous lab. So I will put this thing in the Canvas discussion. Explain why the customer order table is not in the third normal form. So this is the question. Okay, I think that's all for thank you for this week.